Hello, everyone, and welcome to today's media teleconference about the upcoming launch of NASA's PUNCH mission. That is short for Polarimeter to unify the corona and heliosphere. My name is Karen Fox, and I am with NASA's Office of Communications. In a moment, I am going to introduce our speakers, but first, a little housekeeping. You can find PUNCH imagery at NASA's Scientific Visualization Studio. You will be able to find that link in the YouTube description of this live stream. And if you are participating by phone, we are also going to be able to email you that link. You may also find additional resources on PUNCH at nasa.gov/punch. That's spelled P-U-N-C-H, just like the drink. Finally, for media on the phone, please press *1 to get into the queue to ask a question. We are going to start with opening remarks, but we will have time for Q&A after that. All right, so our speakers today, we have three of them. We have Craig DeForest, who is the PUNCH Principal Investigator at Southwest Research Institute. We have Nicholeen Viall, PUNCH Mission Scientist at NASA's Goddard Space Flight Center. And finally, we have Joe Westlake, who is the Heliophysics Division Director at NASA headquarters. And to start off, we are going to pass to Craig DeForest.
Hello, this is Craig DeForest. I am the Principal Investigator for PUNCH. PUNCH is the first mission specifically designed to unify two particular major fields within heliophysics, solar physics and solar wind physics. The solar wind is a stream of material that streaks out in all directions from our star, fills the solar system, and forms the heliosphere around us, giving rise to space weather here at Earth. So until recently, solar physicists could only study the sun and its corona using remote sensing, telescopes of various kinds, radio telescopes, spectrographs. Solar wind physicists, or heliospheric physicists could mainly study the solar wind using direct sampling of material as it sweeps over a spacecraft. Right now, those two fields are merging, and we are bringing that about. I want to explain a little bit. PUNCH is a polarimeter to unify the corona and heliosphere. So what we are about is unifying our understanding of those systems. A polarimeter is a camera that can measure polarized light, like you might see through a pair of polarized sunglasses. And we use that to measure what we're imaging in 3 dimensions. So PUNCH will use 4 cameras that are mounted on 4 spacecraft to image the sun's corona and solar wind together seamlessly to track solar wind features and space weather events in 3D across the solar system. After launch, we'll spread out around the Earth, orbiting over the dawn-dusk line, so that the cameras can view in all directions around the sun. The 4 cameras act as a single virtual instrument to deliver a 90-degree wide image of the entire inner solar system every 4 minutes throughout the mission. So PUNCH is not a telescope to capture images of distant objects. PUNCH is a wide-field viewer that tracks star stuff from the sun as it sweeps over us and over our home. PUNCH is a counterpart to Parker Solar Probe, which you may have heard about. Parker Solar Probe is diving into the corona about 3 times a year to sample the material close to the sun and discern the processes that are happening there. Together, the 2 missions will provide the first complementary data sets showing how the sun gives rise to the solar wind and space weather that span a factor of 1 billion in scale. Applied to biology, that's like tracking and measuring simultaneously the anatomy of a sprinting track star and also the individual motions of molecules of glucose in that runner's muscles. That is a phenomenal range of scales that we'll be able to capture. So PUNCH uses ordinary visible light cameras with exquisitely calibrated photometric detectors to image the very faint sunlight that is scattered off of the solar wind. We have one narrow field imager coronagraph, which is an artificial eclipse in front of a camera. That's built by the Naval Research Laboratory here in D.C., which will look at the corona close to the sun. We also have 3 wide-field imagers, which are deeply baffled cameras built by the Southwest Research Institute. And they will look farther away, up to about 45 degrees from the sun in all directions. In flight, each of the 4 cameras overlaps the fields of view of the other three. That allows cross-calibration. That cross-calibration is important because although the raw pictures will look very much like ordinary star fields, the magic of that mission, or this mission, is the data processing on the ground. We are tasked with removing all of the optical distortion from each of 4 separate physical cameras to produce idealized images from a single virtual instrument. Once we're done with that, the solar wind itself forms only about 0.1% of the light in each image. So we have to strip away 99.9% of the light in every image. That's mostly star field, galaxy, and something called the zodiacal light in the solar system, before we can even use the data. So we were looking at less than 1/1,000th of the photons that land. To give a sense of the technical accomplishments that's required for that, as a side effect of our main science, we will enable new astronomy by producing the world's most comprehensive polarimetric star map of just over 3/4 of the visible sky. So we're very excited about PUNCH and how it'll change our understanding of the world around us. We're going to make the invisible surroundings around us visible. And I hope to share that excitement with everyone in the months to come. I'm going to hand off to our mission scientist, Dr. Viall from NASA Goddard.
Yes, hello. We are very excited about PUNCH and about what we're going to get to see with the PUNCH mission. PUNCH is going to provide unprecedented 3-dimensional view of the corona as it turns into the solar wind and fills our solar system. So if you got to see a total solar eclipse last year as it came across the United States, or if you've ever gotten to see a total solar eclipse, that is like what PUNCH will get to see. As Craig mentioned, this is ordinary visible light that your eye could see if it were sensitive enough. So PUNCH is going to see a total solar eclipse, see that corona, see it as it extends outwards, but it's even better than an eclipse because you get to see it not just for the couple of minutes that the moon blocks out the main body of the sun, allowing you to see the corona, but because PUNCH makes an artificial eclipse, we get to watch it all of the time. And we get to watch it in high definition, and we get to see it globally. And we get to see it more than you usually get to see with your naked eye during an eclipse. If you imagine getting to see the eclipse on an actual sky, what PUNCH gets to see extends all the way from straight overhead all the way to the horizon. That's an enormous volume of the solar system that PUNCH is going to see. So we're going to see, as the corona makes this material that flows outwards and fills our solar system on an everyday basis. And it's always structured. It's never just quietly flowing outwards. Additionally, we're going to get to see the big solar storms, these big explosions on the sun that send mass material, coronal mass ejections, out into the solar system. Those impact our humans that are outside of Earth's magnetic fields, our astronauts, and also impact space weather and our spacecraft. So we need to understand that. What's amazing about PUNCH is the amount of detail that it will get. We will get to see both the global structure of those enormous coronal mass ejections and also the bits and pieces that are small compared to the coronal mass ejection but large compared to the Earth. And that matters for how it impacts Earth and our magnetic field and exactly how that space weather plays out here on Earth. That means that if we understand how these structures flow through the solar system better, we may be able to predict space weather events better in the future because of the understanding that PUNCH provides. Additionally, because PUNCH is such an important part of the heliophysics observatory fleet, it's been working with Parker Solar Probe, which Craig mentioned, how we're highly complementary to Parker Solar Probe. But additionally, we're complementary to an upcoming mission called EASY, Electrojet Xenon Imaging Explorer, which is scheduled to launch no earlier than March. So we'll be up at the same time. And what's really cool about that is our noise, PUNCH's noise, is going to be EASY's signal. So PUNCH looks at the visible light coming from the corona, but we will also see the high-altitude aurora, the northern lights, and the southern lights, because we also go over the South Pole. EASY will be measuring the magnetic field associated with those aurora. So the current systems that connect outer space through the ionosphere. EASY measures those directly, and PUNCH will image the associated aurora with those. So PUNCH is just going to be a really great unifier to connect the corona and the heliosphere, and also geospace, Earth's magnetic field, and even astrophysics. And with that, I think I'll pass it on to Joe.
So I'm Joe Westlake, Director of Heliophysics at NASA headquarters. I just am so incredibly excited about the science that we're delivering on PUNCH. You know, NASA science delivers every second of every minute of every day. We are so incredibly excited about what we are doing here in space, but also how we are really building on the shoulders of other missions, building on the work that's been done for decades within NASA science. You know, we talked about it with Parker Solar Probe, we talked about it with EASY, we talked about it with all of these multitude of missions in heliophysics, in which we're covering the span from the closest to the sun to the farthest reaches of our solar system with the Voyager spacecraft. You know, our heliosphere is this massive, gigantic object that spans so far out from the sun, and PUNCH is going to connect from the closest into the sun to the farthest out. And really just, you know, with that connection, with that scientific understanding that PUNCH is going to deliver, we're just incredibly excited here at in NASA Heliophysics. You know, in addition, PUNCH is the first science mission directorate mission, only rideshare under our rideshare policy. This new way of doing things, it really brings efficiency to our launches. It brings us to where, you know, for every launch that we're putting up, we're ensuring that every piece of mass is used, and we're ensuring that each one of those launches delivers as much science as possible for the benefit of the taxpayer's dollar and for the benefit of humanity. So we're really looking forward to launching along with the SphereX astrophysics mission. And this PUNCH mission really, you know, collaborates with the missions across our heliophysics fleet. We have a large number of heliophysics missions doing unique science across the fleet. This mission really unifies some of these key topics like the solar wind and close at the sun to how it affects us at Earth and space weather. And this really makes new findings about the sun's influence on our daily lives possible. By imaging the sun's corona and the solar wind together, you know, our scientists really hope to better understand the entirety of the inner heliosphere, the sun, the solar wind, and the Earth, as that single connected system. So thank you, and I think at this point I'll pass it back to Karen Fox.
Thank you so much to all of our speakers. If you would like to ask us a question for anybody on the line, go ahead and press *1, and that is going to put you into the queue. And in the meantime, we'll get a little conversation going here to talk a little bit more about PUNCH. And my first question, which really could go to anyone, is PUNCH going to help us forecast space weather? And Craig, you want to jump in on that one?
Sure. So PUNCH is not an operational mission. PUNCH is a scientific mission. We are going to explore the physics that gives rise to space weather. However, that said, we expect that we will revolutionize how space weather is forecasted. We are the first mission to be able to track space weather events in 3 dimensions routinely across the solar system. And we're already working with NOAA to prototype what we can do with that information. We fully expect that it will change the way we forecast space weather in much the same way that geosynchronous weather satellites change the way we forecast hurricanes.
One of the things I love about PUNCH is that it's really going to enable the next level of space weather. Craig really just talked about the big space weather events, which is all we had the capability to model and image previously. But with PUNCH, because of its tremendous resolution, we're going to be able to see the daily driving, the smaller space weather events that constantly impact geospace, the Earth, and Earth's magnetic field.
Thank you so much. Another question we have is about PUNCH's, it's a little bit about PUNCH's title, but tell us about polarization and why we are going to be focusing on that with PUNCH.
Thank you. All right, this is Craig DeForest again. Polarization is something we don't deal with every day unless we wear polarized sunglasses, but it's a property of light. The light can vibrate in different directions That's how a polarized pair of sunglasses removes glare. As glare that reflects off horizontal surfaces tends to become polarized. We can filter out specifically the glare that way. With punch, we're making use of some physics of scattering. Everything we see around us, except for the light source itself, is scattered off of a surface or off of an object that's in space. So as we look at the solar wind, we're looking at sunlight that's scattered off the actual material that we're seeing. That scattering process polarizes the light, and the degree of polarization tells us where the object was in 3 dimensions. So by using 3 lenses very similar to the lenses in polarized sunglasses, our exquisitely calibrated cameras can tell us exactly where each feature is that we see with the mission.
You mentioned the 3 lenses. You also have been talking about how they're 4 spacecraft. Tell us a little bit about why we need all of this simultaneously.
Okay. We have 3 lenses in each spacecraft to capture fully, or 3 filters, to capture fully the polarization of the light so that we can do our work on the ground to separate out that signal. But we need 4 spacecraft, really because we need 3. We have to have 2 kinds of instrument, one that looks close to the sun where it's bright, and one that looks farther from the sun where it's fainter. But the ones that are looking farther away have a problem that there's a planet in the way in the form of the Earth. And so we had to make the instrument either very far from the Earth, which would be cost prohibitive, or we needed to make it as large as the Earth. And to do that, all we had to do was break it into 3 parts and mount it on 3 different spacecraft. So that's why we have 3 wide field imagers, and the one additional is the narrow field.
Thank you. I'm going to put Joe Westlake on the spot. We heard a little bit about how Punch complements Parker and EASY, which will be going up. Can you give us a little bit of an overview of how Punch fits into heliophysics as a whole and the work that we are doing studying the sun and space weather?
Yeah, okay. So this is Joe Westlake. Punch fits into our heliophysics system observatory, which really spans everything from the closest up to the sun with Parker Solar Probe, the ESA Collaboration Solar Orbiter, all the way into the spacecraft and missions that we have residing at the Sun-Earth L1 point, all of the upstream space weather missions like ACE, WIND, other missions like that, all the way into how it connects into our magnetosphere, connects into our home here at Earth, and all of the missions that we have in orbit around the Earth, whether it be MMS or Themis or these missions that are looking at the magnetosphere and its interaction, to the missions that are looking at the upper atmosphere with timed and various other missions that we've had going forward as well with the missions that we have on board the International Space Station. We actually just put up the Codex instrument in collaboration along with our Korean collaborators to work together to create coronagraph imagery, so imagery of the upper atmosphere of the sun, from a vantage point on the International Space Station, making use of that crucial asset in space. That informs our connection from the sun to the Earth, but the sun influences so much more, right? The sun really influences everything out into the solar system, out to the moon, to Mars, to the farthest reaches in the heliosphere. We have the Voyagers. The Voyagers are sitting at over 100 times the distance between the sun and the Earth right now, the farthest thing out that we have contact with and that we continue to receive data back from on the Voyager 1 and 2, 47 plus years old at this point. Super excited about that and excited about the information that we'll get from Punch that's going to allow us to better put the sun-Earth connection in context of the science and of the effects it has on our everyday life.
Fantastic. Thank you so much. Again, for any media on the line, feel free to press *1 to get into the queue. That having been said, we do have a social media question that I want to share with you all. Joe just gave us this list of so many of our heliophysics observatories. The question is, why are so many sun-studying missions in low Earth orbit?
Okay, this is Joe Westlake. On that one, for the most part, it is the closest to us, and it is the most straightforward pathway to space to put something in low Earth orbit. If you want to observe the sun, you need to get up above the atmosphere for many of the wavelengths that we look at, and you need to get up above the places where you would get interference. So going to low Earth orbit is the closest, farthest opportunity for that, right? You could go farther than that, and I'm sure that you would get wonderful data and information back. As you go farther and farther, you run into data rate limitations. You run into some of the complexities of operating farther away from the Earth. And so in many ways, this is, again, the most efficient way for us to do our science, in which we're really putting forward the biggest bang for the buck to put things into low Earth orbit and to put things into that really, the sweet spot between space exploration and being able to only view what you can view from the ground.
All right, I'm going to throw out one more question to everybody to go into a little detail, and then looks like we may be out of questions and be ready to wrap up. So, but what I would like to hear a little bit more about is comparing and contrasting PUNCH with other coronagraphs, including what NOAA has operationally. Nikki already answered a question about the difference between really predicting space weather versus understanding it better. Craig answered that as well. But let's take that a little further and talk about what this can do versus what some of our other fellow agency coronagraphs can do.
I'll kick off. So PUNCH is really intended not to capture the entire corona, but to capture this poorly explored outer region of the corona that we're only just now beginning to really probe properly between Parker Solar Probe and some of the analyses that led to PUNCH. These very outer reaches of the corona and how the corona transitions into the solar wind is really the focus of this mission. Moving farther in requires a different instrument because the dynamic range is so great. It gets very bright very rapidly as you get close to the sun. So we had to cut off the field of view in the outer corona. But there are profound changes that happen between the surface of the sun and about 3 solar radii or 5 solar radii out. There's a region called the middle corona where a lot of coronal mass ejections and other ejecta originate in the corona. PUNCH is not optimized to study that location. SEACOR monitors that location. That's the NOAA coronagraph for the purpose of forecasting space weather. And CODEX is looking in that general region as well for the purpose of studying the physics of that middle corona region. So they're very complementary missions. We need all of them, really, to work together. Dr. Viall?
Yeah, this is Nikki. I'll expand on that and say the global field of view that PUNCH provides all of the time is going to be how we put all of these other pieces of the heliophysics observatory and our partner agencies and what they're observing. It's how we're going to be able to put all those pieces together and really understand how the sun creates the heliosphere and how those structures advect and propagate and deform and move as they come towards the Earth. And so it's really, we call it cross-scale coupling. We're connecting all of these different scales. And you can only do that if you have an imager that has these this high resolution and also the global context simultaneously. And then as we heard Joe talk about, CODEX is one of NASA's latest missions that's also a coronagraph, but it has special filters so that it can see the temperature and the speed of the corona as it turns into the solar wind. And so it's highly complementary to what PUNCH sees. PUNCH does not see those things, but we can derive the speed and then compare it to what CODEX has measured directly and really understand, again, these smaller scale structures and processes as they fit into the global picture of our whole solar system.
And let me hit one other topic on that. When we think about the difference between a NASA scientific mission and a NOAA operational mission, those really create a slight difference in the way that we do things. When we think about our goals of going after the fundamental science, we are in some ways doing experimentation to try and understand the fundamental physics that drives our universe, that drives the solar system, that drives the sun and its attachment to the Earth. NOAA is looking to create operational information of which we can rely on 24/7 to be able to tell us things like hurricane alerts, to tell us space weather alerts and other things. That forces different requirements on a mission like this. We're going after the preliminary science, the initial science that can inform your ability to do research to operations, to take that research and inform operations and how we actually do these operational missions. So this is the first step in that direction, and we really look forward to being able to take some of the discoveries that we make in NASA science and being able to put them and provide them for operational services later on with NOAA in collaboration as a partner to really move that forward.
Thank you so much. Thank you to everybody who joined us today for this telecon about Punch. We are going to wrap it up now. That's all the time we have. So thank you to everybody for listening in and for your interest, and to our speakers for talking about Punch. We do hope everybody will tune in for the launch of Punch along with SphereX. It is currently targeted for no earlier than February 27th of this year, just coming up, from Vandenberg Space Force Base in California. You will be able to watch the launch live on NASA Plus, or if you go to your web browser at nasa.gov/live. And you can find more Punch resources at nasa.gov/punch. Thank you very much.